This lesson. So in this lesson, we're going to go through the second technique in the numerical integration series, which is Simpsons 1/3 rule. Now, in the last lesson, we covered the trapezoidal rule, which we discussed. It uses a first order polynomial to approximate an area under, in this case, the ln of x function between 2 and 4. And we found out that the area under a first order polynomial is a geometry of a trapezoid, and this is where the technique got its name. And we found out that this is simply getting the area of a trapezoid, which is the width times the average height. And we found out that for us to get a more accurate approximation was to use more trapezoids to represent this area. We went through an example of 2 trapezoids, an example of 3 trapezoids. Now, we also discussed that there is another way to get a better approximation instead of using more trapezoids, that we can use a higher order polynomial. Instead of a first order polynomial, we can use a second order polynomial, and this is going to be the topic of this lesson. Simpsons 1/3 rule uses a second order polynomial to describe or approximate the area under the curve, in this case ln of x, between 2 and 4. Now, in this case, I want to signify one thing. When it comes to defining a straight line, we need 2 points. But when you describe a curved line, or in this case, a second order polynomial, you need 3 points. So we're going to need a point at the lower limit, which is going to be f of x naught, upper limit f of x2, and also a middle point f of x1. So we're going to have x naught, x1, and x2 defining the second order polynomial that is going to be getting us the area under the curve. Now, to get this area under this curve, what we're going to be doing is we're going to be integrating between x naught and x2. And we're going to be defining this curved or the second order polynomial with a special type of polynomial called Newton's interpolating polynomial. Now, I'm not going to go through the derivation of this type of polynomial because it's not important for this discussion, but when we integrate this type of polynomial, we get this very simple version of this integration, which is the function of b minus a, the upper limit minus the lower limit, also multiplied by this term here, which is basically a version of the average height for this second order polynomial, which is defined in terms of f of x naught plus 4 f of x1 plus f of x2 divided by 6. Now, there are 2 things that I want to do here. So we're going to go through a few manipulations to this function because I want to show you 2 things. When it comes to the trapezoidal rule, you're going to find that when we're doing a single application trapezoidal rule, we have 1 trapezoid. When we have 2 applications, we have 2 trapezoids. 3 applications, 3 trapezoids. So it has kind of a 1-to-1 correlation. But when it comes to a Simpsons 1/3 rule, actually a 1 application Simpsons, because we are defining a polynomial using 3 points, we have actually 2 segments. So for each application, there is 2 segments. So if I'm using maybe 2 application trapezoid or Simpsons 1/3, now I have 4 segments. If I'm using 3 applications, I have 6 segments, and so on. Which means h that we have defined, the width of the segment in this case, is going to be defined as b minus a divided by n. So in this case, we have 4 minus 2, which is going to be 2 divided by, since we have 2 segments here, divided by 2. So the width h here is going to be equal to 1. So for the Simpsons. So Simpsons, 1 application has 2 segments. So that's the first thing. So I'm going to take this definition of the h as b minus a divided by n, and I'm going to plug it in here, right? So if I do this, this will reduce to h divided by 3. Now, the second thing I wanted to show you is this is where the technique gets its name, this factor of 1 divided by 3. This is where the Simpsons 1/3 rule gets its name. Now, much like with the trapezoid, for us to get a better approximation for the trapezoid, we used a multiple application. We used multiple trapezoids under the area that we're interested in. And the same thing can be done for the Simpsons 1/3. We can actually use multiple application Simpsons. In this case, I'm using 2 applications of Simpsons, and you can see we have here 5 different points from x naught x1, x2, x3, and x4. And since I'm having two applications and each application has two segments, now I have four different segments. And much like with the trapezoid, for us to get the area under here, we just added the areas of both the trapezoids. Now with Simpsons, we're just going to add the area of this application and the area of this application by the use of this equation up here or down here. Now for the first application, the functions are x0, x1, and x2. For the second one, the functions are f of x2, f of x3, and f of x4. So basically we have added this one to this one. Now let's actually do a few algebraic manipulations here, because much like with the trapezoids, because we created this general equation that defines anything, any application of trapezoid, we want a similar general application or general equation for the Simpsons 1/3 rule. So we're going to take the h divided by 3 as a common factor here. And also there are two patterns that I want you to notice. Much like with the trapezoid, there's f of x2 here and f of x2 here, which means it turns into, we have a term that is basically 2 f of xi, much like what we saw with the trapezoid here. But with the Simpsons, there's another thing, which is here, this term here, the 4. So here we have 4 f of x1 and we have 4 f of x3. And if I added another application, I'm going to have 4 f of x5. If I add another application, it's going to be 4 f of x7, which means we have 4 and we have f of x, and it's an odd number, right? 1, 3, 5, 7, and so on. And this is basically what we're going to be defined at I, 1, 3, 5, until whatever number we have here. This is n minus 1. But also, for this term, there's also another pattern. Here, f of x2, which means the next one is going to be f of x4, and it's going to be f of x6, and so on, which means this is going to be defined, this sum term is going to be defined in terms of even numbers. 2, 4, 6, 8, and so on. And where you end will depend on the number of segments you have, and this is going to be defined in terms of n minus 2. Much like with a trapezoid, let's actually see whether or not this equation is going to actually reduce to, say, this one here. Because here, how many segments do we have? Well, we have 2, which means n is equal to 2. Well, if n is equal to 2, you're going to find that 2 minus 2 here, which means we lose this term. And we have 2 minus 1 here, we have 1, which means there is one sum in here, which is going to be 4 f of x1. So it's going to be fx0, 4 f of x1, this term drops out, f of x2, which reduces down to this. So now we have a very simple equation that defines Simpsons 1/3 rule, that is defined in terms of the function that you're interested in getting the area under the curve for, and also knowing the number of segments that you're using. And the number of segments, again, will depend on how many applications are you interested in doing. For Simpsons, if you're doing one application, that means your n is going to be equal to 2. 2 applications, n is going to 4, 3 applications, 6, and so on. Now, what did we learn in this lesson? We learned the second technique of numerical integration, which is Simpsons 1/3 rule, and we learned how to do a single application using basically Newton's interpolating polynomial here, and we got a simpler version of the integral. We defined h in terms of this equation here, which got us this form, and this form basically told us two things: that a single application Simpsons is made up of 2 segments as opposed to a single application trapezoid, it's only made up of 1 segment, and also where the name of the rule came from. Also, we found out that to get a more accurate approximation, we can use multiple applications Simpsons, and in this case we used 2. And basically we used the equation for a single application to add these 2 areas together. And from this equation, we came up with a generalized equation that now is going to represent this technique in future lessons. Well, this will be it for this lesson, and I will see you in the next lesson.